Okay, here in example 1, I want us to graph this, talk about the transformations on the graph, and then discuss all of those key characteristics that we talked about in chapter 1. So log base 2 of x plus 4, and the plus 4 here is on the outside of the function. If it was on the inside of the function, you would see parentheses around x plus 4. You can compare with example 2 and what that looks like to see what I mean, but this plus 4 is on the outside of the graph, and so what that means is that this graph is going to be transformed up 4 from the parent graph log base 2 of x. So you can see right here, I've gone ahead and just written down the base table for log base 2 of x, and now if we want it to be shifted up 4, we're going to have to add 4 to all of the y coordinates. So if I add 4 to negative 2, that's going to give me 2, this is going to give me 3, this is going to give me 4, this will give me 5, and then this y coordinate will be 6. And so if you go ahead and start plotting some of those points, you've got 1/4 and 2, you've got 1/2 and 3, 1 and 4 will be right there, 2 and 5 will be here, and then 4 and 6 is right there. So we're still going to have our vertical asymptote at x equals 0, but the graph is just going to look a little taller than it did before. And so now we're ready to start talking about some of these characteristics that we've been discussing. And so what would you say the domain of this particular function is? Well, the domain starts at 0, but it does not include 0 because of the asymptote, and goes all the way to infinity. The range includes all real numbers, negative infinity to infinity. This is a continuous function since we were able to draw it without picking up our pencil. What is its increasing and decreasing behavior? Well, this graph is always increasing, so I'm going to say increasing here on the interval 0 to infinity. Is this graph bounded at all? Well, no, it is not, so I'm going to say not bounded. Are there any extrema? Remember, extrema would be maximums or minimums. And the answer to that question is no, there is not a max or a min. Does this graph have any symmetry? No, there's no symmetry to this graph. It's actually somewhat of a not very remarkable graph because there's not a lot of these things. However, there is an asymptote, so we have a vertical asymptote at x is equal to 0 for this particular graph, and then the end behavior we'll write using our limits. And so the limit as x goes to positive infinity, we'll just call the function f of x, is equal to positive infinity, since as you go to the right end of this graph, the y values are increasing without bound to infinity. And then the left end of this graph is actually 0. So I'm going to say the limit as x approaches 0 from the right side of f of x, and that is going to equal to negative infinity, since the y values decrease without bound as you approach 0 from the right on the x-axis. Okay, here in example 2, notice the difference between this function and example 1. The x plus 4 now is serving as the argument inside the parentheses here. And so now the plus 4 is not going to move us up, it's going to move us to the left. And so that's going to affect the x-coordinates of the parent graph. And so instead of an x-coordinate at 1/4 or 0.25, we're going to have that x-coordinate be at negative 3.75. Instead of that 1/2, this is going to be at negative 3.5. Instead of 1, when I subtract 4, that gives me negative 3. This will be negative 2, and this will be 0. And so what's going to happen to the graph is instead of having that horizontal or that vertical asymptote at x equals 0, you're now going to have that vertical asymptote at x is equal to negative 4. And so that's going to be right here at x equals negative 4. That will be your vertical asymptote. And then if you plot these points just as best you can, then you're going to see that it looks very similar to the parent graph. It just got shifted over to the left. And so negative 3, 0 will be here, negative 2, 1 will be here, and then 0, 2 will be here. And so your graph will look something like this. Okay, so what's the domain? Well, this time it doesn't start at 0, it starts at negative 4 and goes to infinity. Again, not including negative 4 because of the asymptote. The range will still be negative infinity to infinity. This is still a continuous function. It is still increasing all the time on its domain from negative and 4 to infinity. It is still not bounded. In fact, no logarithmic function is going to be bounded. It still has no extrema. In fact, no logarithmic function is going to have extrema. It has no symmetry, and that will also be true for all logarithmic functions. It has a vertical asymptote, this time at x is equal to negative 4, and then the end behavior will be the limit as x approaches positive infinity, and then we called this function g of x, so I'm going to write g of x there. That's equal to positive infinity, and the limit as x approaches negative 4 from the positive side, or from the right side of g of x, this is equal to negative infinity. Okay, in example 3, h of x is equal to 3 log x. And so the first question you may be wondering is, like, what's the base? There's no number there that indicates what the base is. And so what the base is, whenever there's no number to indicate the base, and it says log, what we're talking about there is the common logarithm, which is base 10. And so this is a base 10 logarithm. Whenever you don't see a number there and it's log, then that is log base 10. And if it makes you feel more comfortable, you can write in a 10 there, just like I did, in order to indicate the base. So what are our x-coordinates on the parent graph? Well, for the y-coordinate negative 2, that's going to be 1 over the base squared, which would be 1 over 100. And then for negative 1, it'll be 1 over the base, so 1 over 10. That x-coordinate is always fixed at 1. For this x-coordinate, we're going to have the base, which is 10, and then the base squared, which is 100. And then what's happening to this graph with the 3 in the front? Well, that is representing a vertical stretch by a factor of 3. So a vertical stretch by 3. And so what that means is we're going to alter our y-coordinates here by multiplying them by 3. And so this is going to become negative 6. This will become negative 3. This will stay 0. This will become 3. And this will become 6. And so just as best I can, I'm going to plot these points. 1 over 100 and negative 6 is going to be about right there. 1/10 and negative 3 is going to be about right there or so. 1, 0 is my familiar point right there. 10, 3 is way down here. And then 106 is obviously going to be way off the graph. I'll just put a point right here to kind of indicate that. But notice again, we still have our vertical asymptote at x equals 0. This is not a very smooth graph. In my drawing, it would be smooth if you graphed it in a calculator, but I'm not as good as a calculator, so I'm just going to do my best. And so there's my vertical asymptote at x is equal to 0. So what is my domain? My domain is 0 to infinity, not including 0 because of the asymptote. The range, once again, is negative infinity to positive infinity. This is a continuous function, so I'm not going to write that because we're going to write that for every example. Every logarithmic function is continuous. This is increasing. I'm going to write that down because there's a possibility that that could sometimes change. This is going to be increasing on its domain from 0 to infinity. There is no boundedness. There are no extreme points, no maxes or mins. There's no symmetry. There is an asymptote. And that asymptote is a vertical asymptote at x is equal to 0, and there is end behavior. So the limit as x approaches infinity of h of x, this is going to equal to positive infinity, and the limit as x approaches 0 from the right side of h of x, that is going to equal to negative infinity. Okay, here on example 4, we've got f of x is equal to the natural log of x plus 2. So you notice I don't have a table here. I'm not going to be that concerned with the table when it comes to natural logarithms because of that e being a decimal, and I don't really necessarily care for you to know the decimals. And this is going to be all non-calculator work anyways, and so I'm not going to expect you to know what those decimals are by hand and by heart. And so just a couple of things I want to point out on this example. First of all, that whenever we talk about the natural logarithm, we're talking about base e. And so you need to make sure that there's a marriage in your mind between e and natural log. Those two things go together. Now, the other thing is that this graph is getting moved to the left too. And so typically my logarithm graphs have a vertical asymptote at x equals 0. But when I move them to the left too, that vertical asymptote gets moved as well. So now my vertical asymptote is at x equals negative 2. Okay, so let's just graph this real quick. Here's the thing, just know what the general idea of the graph is. So the general idea of the graph is that this is going to be increasing. It's going to have its x-intercept is what I'm trying to say. Its x-intercept whenever the argument is equal to 1. So what number is going to make that argument equal to 1? Negative 1 is, and so negative 1, 0 is what's going to be my x-intercept. And then honestly, just get it through that point and then curving around so that it's increasing just like the other graphs looked like. Okay, so our domain, negative 2 to infinity. Our range is negative infinity to infinity. It is a continuous function. This particular function is increasing on its domain. It is not bounded. It has no extrema. It has no symmetry. It does have a vertical asymptote, in this particular case, when x is equal to negative 2. And our in-behavior limits, we'll say the limit as x approaches infinity. We called this function f of x. This is going to equal to positive infinity. And the limit as x approaches negative 2 from the right of f of x, this is going to equal to negative infinity.